Okay, this does not take real long. That's why it's called a quick lab. It says use the following picture to check the reactivity of family 7 elements. So tell your partner where the family 7 elements are. All right, good job. Right next to the noble gases. So what we have here, and there's like draw it out so you can have it in your little assignment. But there's also ones printed that'll be in the lab. So what we have is a petri dish. This is the picture looking down on it. And you're going to put drops of these things in these locations. You will notice most of these have a metal and then a halogen. Metal, halogen, metal, halogen, metal, halogen, metal, halogen. All right. This dye is a acid-base indicator that just changes color over time. It's not really important. It just helps you know when the reaction's complete. Now, honestly, the dyes have changed really slow today and everything else has gone fast, so it doesn't really matter. But what you'll do is you'll use your pipette. You'll put a few drops of NAF and all that around, and then some bleach in the middle. And then the scarier part is you're then going to add a hydrochloric acid. And once you've added the hydrochloric acid, you're going to put the lid on top of the petri dish. All right. Now, if I do a side view, I would now have a petri dish with a bunch of blobs. Then I'd have the lid on top. And then I have created a chemical reaction when I add HCl to the bleach, and it produces chlorine gas. Okay, so the swimmers will enjoy how it smells in here, but everyone else will be like, oh man, it smells like a swimming pool. All right, they'll think, wow, it smells like home. All right, it's not.
I heard that like the chlorine smell actually isn't chlorine. It's like it's how like how much like people use pool and then like actually smell. I haven't heard that actually true.
So there is a thing where your urine does react with the chlorine in the pool to make a smell that you can smell at a swimming pool. But what's that? You can. All right, but there's still a definite odor of chlorine. Yes. Yeah, it's a deadly nerve agent. Okay. Okay. Shh. It's safe, or I wouldn't have you do it. Chlorine gas can absolutely kill you, but the amount we're making is tiny. I don't remember the formula for mustard gas, but yeah, it's a completely different style. Okay. Are we ready? Okay. I should not have said it's not really a nerve agent. It's just a suffocating agent, in case you care. But we're making a small amount. You're not going to mix it in there and then like put your mouth right here and inhale. You'll be fine. Okay. So here's what happens. Chlorine gas will try to react with these things in these droplets like NaI. All right. Now, if a reaction happened, then something will change. And I've said this before. If something changed, then something changed. You heard that before? All right. So let's say one of these droplets turned colors, then you would know the reaction happened. So if this reaction happened, chlorine was able to replace iodine, and we'd have NaCl plus iodine solid. Now, iodine solid is black. So our clear droplet, if this reaction happens, our clear droplet will go like yellow, brown, and black eventually. Okay? Now, it sometimes chlorine will knock on someone's door and it can't react. Like it will not be able to displace the other thing. So what we're doing, we're using this chemistry, this template to see if this supports what we've learned so far. All right? And it should, but think through this, how what we're seeing here has supported what we've learned in this chapter so far. All right, and then for practice, write out, sorry, that's out. Gosh dang it. Write out the reactions that did happen. So we've done that before. If something changed, then something changed. Write out and balance that chemical reaction. Okay, now this tray will be full of little colored dots. What you need to do, so it'll have the lid on still. You'll take it with the lid on, turn the water on, and then you will open it up and wash it out at the same time. Like just open it and rinse pretty quick. Make sure the water's not on super fast so you don't splash on you because it will hurt your clothes. All right, here's the papers. I use this in normal chemistry. There's the paper right there you can set it on. And just literally put the dots. Easy enough. All right, now, most of the solutions are right here on this table, but the bleach and the acid are in the fume hood. Don't add the acid to the bleach until the last step and you're ready to put the lid on. Now, just for a public safety announcement, don't ever put an acid and a bleach together. It can kill you. All right. Now we're putting 3 drops. We're gonna be fine. What? No, the gas will kill you. So this happens in the United States thousands of times a year. It usually happens in your shower when you're cleaning it, because you get in a confined space and you use some sort of cleaning agent and that didn't work very well. So then you switch and then you don't realize it. But in that little shower, you've now created a little area full of toxic gas and you'll pass out first and then you continue to breathe and you just die. So don't ever mix chemicals when you're cleaning. And even if like you put bleach in your toilet to clean it, you should flush before you urinate because even that can create gases that are not good for you. So be careful. What? 0, probably 0. Okay, you need safety glasses. The safety glasses have to be decontaminated every time you use them. So you grab from that and then you'll return to the basket that's in this one. This is from last hour. We'll dry those as you do your lab. Okay, questions? It doesn't take long. Think about everything we've learned so far and what this, these reactions do to support what we've learned so far. Okay, ready, set, go. All right, TA, grab that rag. So that's the bleach water. This is our rinse water. And then we just have to dry them. So once you've dried them, just drop them in that far bucket. You're the best. All right, I don't know. Is this orange right here? That's probably orange, right?
Yeah, I think it's orange. Well, CL is the same as CL.
It's good enough. Okay. We all right with that? Just about like that, correct? All right. So that would mean you need 3 equations. You don't have to write out the equation for dye. I should have told you that to start with. But I don't even know the formula to universal indicator. It's made out of like 10 things. So we wouldn't need to do that. But so just looking at this one, something changed. So in the chemistry, something changed. So this reaction did happen as written. Chlorine gas reacted with sodium iodide. This is technically aqueous. All right, to form NaCl, aqueous, and iodine solid. If you leave it long enough, it'll start to turn black. Did anyone see it getting really dark brown and black? Okay. So as the iodine solid comes out of the solution, that's what causes the color to change. So in this reaction, chlorine was able to replace iodine. Okay, another one, chlorine, whoops, plus NaBr made NaCl plus Br. That'll be Br2, sorry. And this would be a liquid, and this stuff's yellow. So that one should have turned yellow, maybe a tiny bit brownish yellow. All right, and I have not balanced these. You should balance them. They're not real super hard. But this reaction, something changed. Whoops, push the wrong button. Okay, something changed, so something changed. And what changed was the ion in solution. So what we learned is chlorine could replace bromine or bromide, technically, in this relationship with Na. So here's what's really happening. Chlorine, that's sodium. Sodium has an electron to give away, right? And it has shared it with bromine originally. But when chlorine gas comes to town, it is able to steal that electron because chlorine is more reactive than bromine. Once it steals that electron, bromine now has to find another partner and become its elemental form. Whoops, liquid, bromine liquid. It's not positive, it's neutral. It's what it is as an element instead of an ion. So what we learned is chlorine is a bigger bully. It can take the electron that sodium wanted to give to bromine. It's like you go to a sporting event and the athlete goes to throw the t-shirt to the kid in the one row, and then the 6'3" big dude just like stands up and takes it. Yeah, it just, that's what chlorine does, because sodium's like, here, bromine, and it's like, no.
Wait,
I will take that.
yeah,
What's that? Okay, so let's get there. So the one that would not happen, go ahead.
So is it just because
Whoops.
it's like a shell higher on the periodic table, you could say? So actually that barely has a higher nuclear. I thought they all had the
It
same
has
nuclear
a-
charge. They have the same.
it has a higher Zeph slightly.
Listen,
Slightly. And then
the
also has
numerical value of Zeph is the same, but its size is what matters now.
So BR is slightly larger.
What's that?
So BR would actually be
Yeah, bromine's bigger, so it's kind of the reverse of the example I used.
So
But chlorine has a better pull.
the smaller the atom, the more reactive it is.
Well, it's kind of screwed up in our world. Because explain me this. The smaller the atom, the more reactive, and the bigger the atom, the more reactive, which seems to just blow everything up. But it doesn't. Walker, why?
So it's like the atoms like on this, like the bottom of the left are reactive and the up on the right.
Yep.
And then everything in between is less
But
reactive.
you're saying it should blow everything up, but it doesn't.
Everything else is a victim.
Yeah, he's asking why.
I know. I don't know why. We've talked about it.
Does it have to do with electron spin at all?
When it's higher depth, when it's like this bigger.
It's
Okay.
because one, they're more reactive because that one's the one that gives it away the most, and the other is the one that takes it the most.
Yeah, so it's like the ugliest and then the most
Yeah, so it's like
effective.
Biggest Loser version. It's like Biggest Loser. So like
Versus
they win.
biggest taker.
Okay.
Yeah.
Biggest Loser and the Olympics. That's what we're comparing right now.
Okay. So in our weird,
Another side of it.
in our weird world of chemistry, we can say the sentence: the smaller, the more reactive; the bigger, the more reactive, because one rule applies to losers, which we also call metals, and the other rule has to do with takers, which we call non-metals. There's no reason you can't have both of those. This thing wants to lose, so the bigger it is, the easier it is to take away. These want to gain, so the smaller it is, the more attractive the electron is to their nucleus because it's closer. Yep. So we were able to see this happen in the lab. Oh man, I keep bumping that. My finger's a little lower than normal or something. Okay. We were able to see that because this reaction, did anything change? Nope. So if nothing changed, then nothing changed. And that meant that fluorine, of everything we tested, fluorine was the, oh my goodness, fluorine was the only thing bigger, well, I shouldn't say bigger, that was more mean than chlorine. Go ahead. What's that? Oh, did I, what am I doing? Sorry.
We put NaCl.
Sorry.
Cl2.
Oh, I'm sorry. That's supposed to be in there.
Salt plus chlorine.
So
Oh
this is
my
like-
gosh. What?
I love salt.
The chlorine did not react. The fluorine,
Yeah, chlorine.
fluorine is way smaller, way more electronegative. Chlorine cannot replace fluorine. It just says no.
So the whole Z thing kind of explains electronegativity.
It explains electronegativity. It explains size. It explains like ionization energy, and it will lead us up to this idea of electron affinity. Okay, I need to give you some points. So make sure your name's on this and you turn it in before you leave.
When we did the redox reactions, was it the same, like how we said lithium to loser and like gold?
Yep.
Is it on this?
Yep, the ease of oxidation is the same idea here. It's your ability to lose an electron. This one's just your ability to gain. So it's the same idea, just the reverse explanation. Yes, Judah. Yes, you can. All right, that was all I had, TA. Thank you.
What color did oh, it's probably the same.
Are we out of here? Okay. We got like 15 more minutes, I think, or at least 10. Okay. So a lot of times in chemistry, we can tell you stuff, but we don't get to see it. This one, you were literally able to see proof that fluorine was more reactive than chlorine, that chlorine was more reactive than bromine, that chlorine was more reactive than iodine.
And you could do this for the whole entire family, huh? And then
Yeah, you could. Oh.
Why were some clear then and some didn't really have a chemical reaction?
The ones that stayed clear, this one, if chlorine in this reaction, if chlorine replaces chlorine, there won't be any change because it's just chlorine. In this reaction, it did not have the ability to make fluorine leave the sodium and become its own element. So since there was no change, there would be Yep. There wouldn't be any change. Okay, we all right with that? All right, let's now talk about the least important part of this chapter. Now, it's still something you should have an idea about, but we talk about it the least. It's tested the least, but whatever. Electron affinity. Most often in chemistry, we use the term called electronegativity, which measures, like as Bert says, the hotness of the element. It measures how much it will take an electron to itself when it's bonded with something else. Electronegativity and electron affinity are very much tied to each other. Also, electron affinity is the complete opposite of ionization energy. Ionization energy is the energy required to remove an electron. Electron affinity is the energy released when you add an electron. All right, so right there. Energy change accompanying addition of electrons to gaseous atoms.
So if you knew the ionization energy, you would know the electron affinity?
They're not exactly the same values.
So that's why like no energy released when you combine sodium.
Yep. Well, but there's a third piece of the puzzle we'll learn about called lattice energy. That's actually a really important part of that puzzle.
Is that like the energy, like
the structure.
It's the one that's given off is strictly heat.
Yeah, that's what I meant.
Okay, then yes. Okay.
Yeah.
So when we look at an ionic compound, like just NaF, we were just talking about that. How about that? So we have Na. We would typically lose an electron. So we would talk about the ionization energy required to remove the electron to make Na become positive. But we wouldn't say the ionization energy for fluorine because it was not ionized. It gained an electron to become negative. So we call that the electron affinity. Affinity means like how much you like something, essentially. All right, so when they come together, we can do a little bit of math here. There is a third piece of the puzzle too, though. But it's just the idea, ionization, removing, affinity, adding.
Oh wait, so all isotopes that are
Not isotopes, ions.
ions that are cations, the positive ones.
Yep.
So all cation are always going to be with ionization, and then
Pretty much.
anions will always be with
Affinity. Yep, because they went through those two things. They lost or gained. All right, Marie, we'll miss you. Just right there, that desk will be perfect. All right, so here we go. In general, and this is always in chemistry, we put in general because there's always discontinuities. In general, electron affinity becomes more exothermic as you go from left to right across a row. All right, so what that means is if fluorine were to gain an electron, it would give off 328 joules. Versus if lithium were to gain an electron, it would give off 60 joules. So as we go this direction, generally electron affinity goes up. Now, just sort of stick with me here. This part, I don't know, it's not that tricky, but we learned that size, that over here they're small, right? And over here they're big. So if I were to draw lithium, so Li, I don't know, just comparatively, I'd say there's the nucleus. Lithium is like this big. Am I right with that? Then I'd say fluorine is like this big. Oh, thanks, circle tool. That didn't work very well. All right, so it's smaller. Are we okay with that? Okay, now, if this part doesn't make a ton of sense, it's okay. When we measure electron affinity, we're measuring the energy released when an electron out here in the middle of nowhere goes towards and ends in this outer ring. If I have the electron out here in the middle of nowhere, it will fall farther because fluorine is smaller. If it falls farther, it gives off more energy or is more exothermic. So even electron affinity is still tied to size, and size is tied to Zeph. They're all tied together. So lithium would be less exothermic because an electron would fall less distance towards the nucleus than it would if it went towards a smaller fluorine atom. It's giving energy off by moving closer to the atom. Energy is released. Yeah, it would give off light or microwave radiation, depending on how far it fell. Infrared, any of those types of magnetic radiation would be emitted. Now, most of the time, we observe this as infrared radiation that warms stuff up. So if I were to take fluorine and react it with lithium, the reaction would glow really bright and be really hot. All right, and I would actually see the light produced from this actual process. We sort of okay with that? Okay, I might as well. I don't have those, but I have something else I can demonstrate with, which you've probably already seen. I don't remember if I've done it or not. Hold on. But we can see this energy given off in this reaction. So what I have right here is a piece of magnesium. Have I done this in this class before? Okay. No, I mean, it's not cheap, but comparatively, it's really not that expensive. Oh, that looks safe. Hey, no, I did not. No, it went off. It went off because, oh, you know what? Sorry. Over holidays, I always turn the gas off just in case. What? Why are you so scared? Oh, okay. Oh, this is awesome. Oh. Okay. Okay, hold on. Let's see. Here we go. Now, it's important that you don't stare at this while this reaction happens. But we're going to see radiation given off as an electron goes from far away to close.
Oh, yeah.
You'll see.
Wow, that's bright.
Don't
Don't look.
really look at it.
That's so bright. I want to look so bad.
You can sort of see it though without looking, right? Okay. So what we're seeing, okay, you can look now. Let me do it over here so you can kind of see when it lands. It just crumbles. Okay. So what this is the reaction of when I burn magnesium in the presence of oxygen. It's called magnesium oxide. And I saw light or electromagnetic radiation given off as I converted this to a powder. Oxygen is. So what happened? Oh, I just kicked something.
Did the electron from the oxygen fall into the
Other way around.
magnesium?
Yep. So magnesium gave its electron to oxygen. In fact, it gave 2 electrons to oxygen. Those electrons fell from here towards the highly electronegative or high electroaffinitive oxygen. And we were able to see that energy actually given off in the form of heat and light. Okay. Now, let me go back to the screen share. So like chemistry is just a bunch of ideas and math, I know that, but it is stuff we can actually observe. That's how it started. People saw stuff and they wanted to explain it. Not we came up with crazy explanations and then we wanted to prove it. All right, it seems like this class, but whatever. Okay, here we go.
No.
Imagine being that genius.
All right, there are 2 discontinuities that I do not test you on. They're between here and here and here and here. So the first occurs between group 1 and 2a, and that's because the added electron must go into a p orbital, not an s orbital. All right. So it seems like life should be all great, but adding 1 here is less electronegative than adding 1 there was. That's all that's trying, not electronegative.
So it gets off of
Exothermic is what the word I was looking for.
So it's less energy.
Right. Okay, tomorrow we'll wrap up. There's like 5 slides left, and we're going to test on Friday. Put them right here on this little table right here. Test is on Friday. It's a short test, so don't have a heart attack. Not hard or way hard? You mean the one I wanted to kill all the kids that complained about it? Yep.
I forgot about it.